For centuries, we have modeled the inner solar system as an isolated, perfect clockwork. The orbits of Mercury, Venus, Earth, and Mars appear locked in a permanent gravitational equilibrium, oscillating smoothly without end. But this isolation is an illusion. The threat to this clockwork does not come from inside the system. It comes from stars passing far beyond our outer planets. A recent finding from astrophysicists Garrett Brown and Hanno Rhine shows a distant stellar flyby perturbing Neptune's orbit by just 0.1%, creates an order of magnitude spike in inner planet destabilization. Tracking the x-axis, this probability accrues over a 5 billion-year timeframe. In celestial mechanics, destabilization means the orbits of the inner planets rotate, elongate, and cross. It eventually results in Mercury and Venus either colliding with each other or being ejected into deep space. The solar system's lifespan is entirely dictated by its external galactic environment. To accurately calculate the survival of the Earth, we must discard the concept of planetary isolation. Our planetary system sits within the Milky Way, a massive, rotating host environment. Mapping how this environment interacts with our Sun requires reconciling a paradox. The Milky Way operates simultaneously in two conflicting physical regimes. On the macro scale, the galaxy contains hundreds of billions of stars. At this distance, their individual gravitational fields blur together, forming a smooth, collisionless fluid. Zoom in, however, and the microscale reveals a chaotic n-body minefield. Here, the galaxy is composed of discrete point masses, each exerting sharp inverse square gravitational forces on one another. To understand why a star passing light years away can rip our solar system apart, we have to mathematically deconstruct how a star navigates the smooth macrogalaxy, and what exactly happens when the discrete microreality interrupts it. We begin by looking at how an individual star navigates the collective gravity of the Milky Way. In the macro regime, we treat the star as a test mass. Its own gravitational pull is mathematically negligible compared to the combined mass of the smooth background potential it travels through. Analytical mechanics models this motion using the Lagrangian, an equation that balances the star's kinetic energy against its potential energy. This chart displays the effective potential, the mathematical framework governing the radial boundaries of a star's orbit. The curve maps the potential energy across different distances from the galactic center, dipping into a deep central well. Notice the steep wall on the left side of the graph. Because the star has angular momentum, it hits a centrifugal barrier, an outward force that mathematically prevents it from simply falling into the galactic center. The absolute minimum of this potential well represents the lowest possible energy state. If a star sits exactly at this minimum, its radial kinetic energy is zero, resulting in a perfect circular orbit. But if an interaction alters the star's total energy or angular momentum, it jumps to a completely different potential curve, permanently changing the eccentricity of its orbit. In a perfectly smooth macrogalaxy, a star's orbit is a stable, eternal oscillation trapped within this specific mathematical well. We can apply this exact framework to the Sun's current motion through the Milky Way. This diagram uses the epicycle approximation to map near-circular orbits. It displays the Sun's base trajectory as a perfectly circular reference orbit, rotating at a specific angular velocity, denoted by the Greek letter omega. The Sun does not track this circle perfectly. It continuously falls in and climbs out of its effective potential well, oscillating radially at the epicycle frequency, or kappa. This traces a wavy rosette-style path. Based on observations of local stellar velocities, the harmonic ratio for our specific solar neighborhood is approximately 1.3. For every full orbit the Sun completes around the galactic center, it bobs in and out radially 1.3 times. This clockwork epicycle motion describes the idealized mathematical state of our Sun in a collisionless galaxy, but it ignores the gravitational reality of the billions of discrete stars occupying the exact same space. To see exactly where the smooth approximation breaks down, we have to zoom in to our immediate stellar neighborhood. On the microscale, the fluid-like background vanishes. Our Sun is constantly reacting to the localized inverse square gravitational forces of individual neighboring stars as they pass by. This diagram maps the mechanics of a weak encounter. The subject star moves along a straight trajectory with a velocity v. The closest point it reaches to the passing field star is defined by this perpendicular line, called the impact parameter, or b. As the subject star flies past, the field star exerts a perpendicular force vector that physically pulls it off its path. This force peaks precisely at the moment of closest approach. To calculate the total change in the subject star's velocity, we take the time integral of that perpendicular force, tracking the interaction from negative infinity to positive infinity. The math resolves into a specific equation. The velocity deflection is inversely proportional to both the impact parameter and the relative velocity. The closer the passing star and the slower it moves, the harder it yanks our star off course. Every passing star, no matter how distant or fast, injects a calculable permanent velocity deflection into our local system. The smooth model is constantly being fractured by these discrete micro-encounters. We can now apply this velocity deflection directly to the solar system during a stellar flyby. Our system is not a single point mass. The Sun and Neptune are physically separated by 30 astronomical units. Because of this spatial separation, the Sun and Neptune present different impact parameters to the passing star. According to our equation, a different impact parameter dictates a different velocity deflection. The field star accelerates the Sun and Neptune by unequal amounts. This differential kick physically stretches the architecture of the solar system, expanding Neptune's semi-major axis by that critical 0.1%. A weak stellar flyby does not violently strip planets away into the void. It injects a microscopic differential velocity, planting a permanent seed of secular instability at the very edge of the system. To see the consequences of that microscopic perturbation, we have to fast forward millions of years. The solar system is connected through a mechanism known as secular resonance. The gravitational pull of the planets on one another creates a coupled network, linking the massive outer gas giants to the small inner terrestrial planets. This model processes that 0.1% stretch. Over immense timescales, it transfers angular momentum from Neptune inward to the Sun. Mercury and Venus absorb this energy. Lacking mass to stabilize it, their eccentricity spikes. Their paths elongate, warp, and cross. The gravitational architecture of the solar system acts like an amplifier. It takes a microscopic orbital nudge at the galactic edge and steps it up into a chaotic collision at the center. We return to the view of the Milky Way in its entirety. By definition, the relaxation time of this galaxy, the time required for star-to-star interactions to completely randomize stellar velocities, is over 100 times the current age of the universe. That immense time span makes the Milky Way technically collisionless on the macro scale, but the micro scale tells a cumulative, deadly story. The slow accumulation of these weak two-body stellar encounters simply never stops. It is the ultimate, unavoidable clock ticking down on our planetary system's lifespan. The long-term survival of the Earth cannot be calculated in orbital isolation. Its fate is inextricably bound to the chaotic, discrete mechanics of its host galaxy.